In this video, we are going to be looking at an example for an ideal gas law problem. Okay, so first of all, let me explain to you that again, the ideal gas law is like this, wherein you combine all the four quantities. So P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. And again, if you change the pressure into another state, the third state, then all the three states, as long as you do it this way, pressure times volume divided by number of particles over temperature, this is all, sorry, this is supposed to be 3, like that, they're going to be equal. And again, you can do 4 states, 5 states, 6 states, but the thing is, when you divide this, it will equal a number, and that number is this, which is 0.0821. If you divide this, so let's say you change the pressure, you change the volume, you change the number of particles, you change the temperature, no matter what those changes are, when you divide, when you calculate the 4 through this equation, P times V divided by N over T, divided by N divided by T, the answer is going to be this number, which is 0.0821, as long as you are using ATM for the pressure, liter for the volume, mole for the number of moles, and Kelvin for the temperature. So usually, because you already have the four equations, right? So normally, let me take for example the combined gas law. In combined gas law, you have something like this, right? Where you rely on an initial state and a final state to solve for something. So for example, this is given, 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 and then unknown, and then given. So in order for you to solve V2, you kind of need first state and a second state, and then you kind of solve this one. But for ideal gas law, P1 V1 over N1 T1 is equals to P2 V2 over N2 T2. It's not necessary. Why? Because again, as we said, this equals to that number, and this also equals to that. So instead of P1 V1 over N1 T1 is equal to another state, we simply just replace this with that number. Okay? So we simply say P1 V1 over N1 T1 is this number, which is what we call R, which is the gas constant. And again, because we are only now in our equation, we only have one P, one V, one N, one T. It doesn't really make sense to label them as one, because we only have one pressure, one volume, one number of particles, and one T, one temperature. So we now have this equation, which is P over V, P times V over N times T is equal to R, which is the gas constant, and that gas constant is like that. So let me rewrite that here, and let me rewrite that as P over V, P times V over N times T is equivalent to R, where, again, R is always equal to that value, which is, if I'm not mistaken, is 0.0821 ATM dot liter mole Kelvin. Okay? And again, in some books, usually they kind of write this as PV equals nRT, right? Which is really the same. It's just that I like this because it reminds me that it reminds me of the other laws, which is the combined gas law. Remember, the combined gas law is just P V over T, and then Wolff's law is just P times V. Charles's law is just V over T, and Gay-Lussac's law is just P over T. So again, this formulation kind of reminds me of the other gas laws. That's why I don't prefer this, but it's the same, obviously. So here you have a problem where, for example, you say, what if the pressure is 2 atm? What if the volume is, say, 600 ml? What if the number of particles is 3 moles? The question is, what will be the temperature? Okay? What will be the temperature? So maybe let's change that. Maybe let's have here the temperature is 30 degrees Celsius. The number of particles is 3 moles. And then the volume is 600 ml. And then we are going to solve for the pressure. Okay? So again, the same thing applies as what we have discussed in terms of problem solving. Number one, are your temperature units in Kelvin? Unfortunately, nope. This is a red flag because this is in Celsius. So what does that mean? That means you have to kind of convert it to Kelvin. Second, are you consistent with your units? Well, remember your R here has the units. It dictates already the units. The pressure is in ATM. The volume should be in liters. The number of moles should be in moles. And the temperature should be in Kelvin. So here, you see a second problem. That second problem is you're not consistent with your units because here it's in ml, but in your R, it's in liter. So what does that mean? You have to convert that to liters first. Okay? So once you converted, so you have to convert that. So let's do that quickly. So again, for the liters, you just have the conversion equivalent that every liter is 1000 ml, right? So therefore, 600 ml, again, simple. You just take what you want to convert, multiply it with a conversion equivalent, which is this one, and you just have to cleverly arrange them. Obviously, I'm going to put ml here and liter here so that the ml gets cancelled out. So ml is 1000, liter is 1. So ml gets cancelled out. That gives me 6,000 times 1 divided by 1,000. That's 6 liters. And now I know that this 600 ml is 6 liters. Right? And then now the temperature, which is 30 degrees Celsius. So I know that temperature in Kelvin should be equivalent to temperature in Celsius. And again, there are plenty of ways to do this, but I can do this by converting. And again, saying that for every 100 every 100 steps of Kelvin, there are 100 steps also in Celsius. And then again, remember, Celsius has a disadvantage. Remember when Celsius is at 0 Kelvin is already 273.15 degrees Kelvin. So it has a disadvantage. So you have to add that disadvantage, which is 273.15. And remember, this is already in Kelvin because you cancel out the Celsius. This must be in Kelvin. So now you replace, you say, well, that was 30 degrees Celsius times 100 Kelvin over 100 degrees Celsius. Obviously, that's just the same number, 273 Kelvin. So that gives you 30 times this, which is around 303 point, yeah, 303.15 Kelvin. So that's your temperature in Kelvin. So that gives you 303.15 Kelvin. Okay? So now that you have that, obviously you are going to solve for it. So let me just use this space here, right? And then you say, well, I'm solving for P. So let me change everything here, and that would be P is equal to nRT over V, right? See, the V must be transferred to the other side, the denominator. This 2 must be transferred to the numerator on the other side. So that's it. So now you have the number of moles, which is 3 moles. You have the R, which is uh, 0.0821, and then the unit is ATM liter mole Kelvin. And then you have the temperature, which is 303.15 Kelvin, right? And then you divided it by the volume, and the volume here is 6 liters. Okay, and then let's stop for a while here and look at the units, right, on the numerator, because it's kind of confusing. So you have mole, which is in the numerator, and then that gets multiplied by ATM liter over mole dot Kelvin, this second one, and then the third one is in Kelvin. So notice again, implicitly, this is mole over 1. This is Kelvin over 1. So you notice that the mole here is a denominator, numerator, cancel out. Kelvin is denominator, numerator, they cancel out. So now what is left at the top is just ATM and liter. Okay? It's just ATM and liter. So here, you can say that what is at the bottom will be, at the top will be ATM that liter, and then what is at the bottom will only be liters, and then what is at the bottom here is obviously 6 liters, and then here we have to multiply that. So let me get my calculator real quick, if I can find it. Where is it? It's here. So let's have 3 moles, right? Multiply that with 0.0821, and then multiply that by 303.15. So that gives me 74.665845 ATM liter. And as you notice, the liter cancels out, right? And then finally you have the pressure, which is now this one divided by 6. So divided by 6. So the answer would be 12.444375, and then what is left is ATM, right? And then in here you can do a lot of things, but normally what is the custom is to just kind of round it off to the second decimal place. So this is 12.44, so just leave it as 12.44 as the final answer, and this is in ATM, and that's the idea. So in this example, I hope you kind of got the idea of what I have been talking about. So number 1, that every temperature scale must be converted in Kelvin. Number 2, that you have to be consistent with your units, since the given volume is in ml, but in your R, what is incorporated in that unit is in liter, so you have to convert that to liters. And then second one, you have to show me the conversions. I showed you the conversion in the smaller whiteboard a while back. And then after that, you solve following the cancellation of units, and then get the final answer here. So take note that you will only get a perfect score in your worksheet if you show me every step in the calculation. So again, this is not about you being able to answer, to give me the correct answer. This is about you being able to communicate to me how you did it. If you can't communicate it to me, it might as well be that you were not able to get the correct answer. So it's a skill also that you should learn. You don't only need to know the answer or calculate for the answer, but you have to know how to communicate how you calculated the answer to other persons, namely to your teacher. So let this be a guide for future calculations involving ideal gas law.